Hi, today we're going to move a little bit closer to fully being able to address that question of steel wool on the scale. I think it's best to shift gears a bit and start talking about chemical reaction. So as you can see by the title here, there are two substances going to be involved in this reaction, potassium chlorate and a gummy bear. So take a watch and write down any questions you have. So that's fun. Actually, I've done this reaction before. You have to be careful. The test tube can melt. There's that much energy involved with this. And what I have here is one more video of the same exact demonstration. This one says potassium chlorate at the top. This one says sodium and. So on the left we have sodium chlorate, and on the right potassium chlorate. Same exact reaction, except I think this one's giant gummy bears. And you can see the only difference is the color of the flame. In both cases, you get a very vibrant flame, but clearly on the left we have a very bright yellowish-orange flame, and on the right that purpley lilac color, which is, those are indicative of those group 1 ions. We know we put in potassium chlorate, and there was a gummy bear put in, and gummy bears are almost 100% sugar. Although if we're going to be talking about chemical reactions, it would probably be beneficial to turn them into chemical formulas. Now what we don't know is what it turns into and what information we can gather from that. But we know those two substances went in. We know that it was kind of hot, so it was heated first. But I think our goal for today is by the end of this we should be able to finish up this chemical reaction. What were produced, what products were made, and can we balance it, and what do we know about this kind of reaction, and how can we describe it? So I think it's beneficial to first talk about the types of chemical reaction and how we can classify chemical reactions. There are two main ways that we categorize these reactions. It's based on the nature and number and type of the reactants going in and any observations we have over the course of the reaction. The 5 types of reaction are listed there. I'm going to abbreviate them for ease of discussion and labeling here. Feel free to write them out, of course. For each case, I'm just going to quickly label them so that we can get them categorized for your notes. The top one being combustion, then decomposition, synthesis, single replacement, and the bottom 2 are both double replacement. And you're responsible for being able to look at a balanced reaction and categorize it just based on what's there. And so to make that process a little bit easier, I thought it would be a little beneficial to maybe translate these into general forms that we could use moving forward to say, it fits this style of reaction. For the synthesis reaction, that's 2 different chemicals, we'll just call them A and B, coming together to make a compound, AB. For this top one here, decomposition, it's the opposite, where one chemical breaks down into 2 different substances. You can notice both of these because this would be 2 substances becoming 1 and 1 becoming 2. The other reactions don't have that general format. The third one here is single replacement I'm going to talk about. This one. So we've got A, B, a compound reacting with some substance C, and it seems like we're making A and CB. So you can see that, that this substance here, this element, it's a compound and an element reacting, and the element it seems to bump in and take the place of one of the elements in the compound, single replacement. For the double replacement, it's a little bit harder to see what's going on, so I color-coded things for you here. If we were to label them like this, we're going to say that these polyatomic ions get labeled as one thing, because you can see, just like we saw before in the balancing, that the polyatomic ion didn't change as the result of the chemical reaction, so we're going to consider it as one object. And then to finish this would be this. It does seem to be the case that for a double replacement, the elements in front switch. Both single and double replacements I will talk more at length about later, so we're not going to worry too much about them now, but again, we get this AB plus CD yields CB plus AD. Again, we've just swapped. You could consider that we swapped the anions instead of the cations. The end result's the same. For a combustion reaction, it doesn't really fit a similar style of description as well, so I think we'll talk more about that in a few slides. But I wanted to approach this in something of a logical order, at least in my head. Before we get too much further, I did want to bring into the discussion this concept of energy. We have kind of touched on this idea a little bit, but it's going to keep coming up as the year goes on, so I wanted to make a more firm foundation here. In terms of energy and chemistry, and the way we've talked about it so far, we've said that elements bond to gain stability. And we've also said before that high stability is synonymous with low energy, which of course would stand to reason that then low stability corresponds to high energy. What we can see here is that the presence of the Bunsen burner adding heat into the substance, that would be increasing its energy. So we are decreasing the stability here by adding in energy, if you want to just think about it very simply like that. What we have on this image here that keeps playing is a reaction between solid iron and solid sulfur to make iron sulfide. This seems to be we get from two elements making a bond, and you can see as the glass rod is touched to the mixture, a large amount of energy is released. So to coalesce all that together into a single statement, it seems to me that breaking bonds absorbs energy, and making bonds releases energy. This may seem like an overly simplistic view of things. If you start with this as a foundation and build on it, it's more that complex systems have series of these happening concurrently, which is absolutely what we're seeing in this bottom image. You're seeing both breaking and making at the same time, and it gets a little complex, but just resting on that one idea will get you pretty far. Is pretty important to breaking things down in the future. So first, I wanted to step in a little bit closer. These are synthesis reactions. So general observations is that it seems to be that energy is released as the synthesis reaction happens. This is a reaction between sodium and chlorine to make sodium chloride. You'll notice that the chemical formulas don't always line up between reactants and products. We've spoken about this in terms of balancing. So it's always good to step back and make sure that your equation is balanced, but that remember that the chlorine is a diatomic element, so it always exists as Cl2. But chlorine and sodium chloride, each ion here, we've got a +1 and a -1. So the ratios of elements in certain compounds can differ from other compounds. Our general form here was A plus B creates AB. Sometimes you'll see that written as C just to denote a different substance. As it says up here, and as you can observe, because we are making bonds, energy is released. For decomposition reactions, it is the opposite. Energy is absorbed to break your bonds, and then in terms of a chemical description, we've got one substance breaking down into two. That said, you could have the situation where one of these two substances that it's broken down into is not always an element. You're not always breaking down one compound into several elements. That does in fact happen. You could see there is a process where liquid water is broken down into hydrogen and oxygen. We're going to have to balance this, of course. That process is called hydrolysis, but it is a decomposition reaction. You usually have to pump electricity into the water to make it happen. But it's also the case, like that we saw in the video, where an element will break down to make an element and a compound. So it's really hard to say that there's one way that these reactions always look, other than to say one substance and two substances, as long as we don't forget that certain times a substance may in fact be a compound. I'll make sure this is balanced. And yes, it does seem to, like the two examples I just pulled, it did work out that oxygen was a product in both. That's not necessarily any sort of hard and fast rule. But this is what we can see going on here during this heating process. A decomposition occurs where potassium chloride breaks down to make potassium chlorate and oxygen. And then finally today I wanted to talk about combustion. Obviously, you can see here several examples of combustion. The big observation here, fire. You see some sort of fire going on. There are many and varied combustions going on here. The one thing you need to know about combustion is that there are two things needed for a fire: fuel and oxygen, the fuel being something to burn. In this case, actually, the fuel was the sugar. In this case, it's probably an alcohol vapor. This is, I believe, phosphorus or potassium chlorate or something, or maybe the wood is actually acting as a fuel as well. And over here we have some magnesium. So whether or not it's super obvious, there are actually two main types of combustion that you'll see. There are reactions in which there's a metal fuel, like on the bottom right here. This is magnesium burning. This one you can do. It's just very bright, so it might be damaging to your eyes if you ever have carried this out on your own. And then organic fuels like, say, hydrocarbons, which are compounds that only have carbon and hydrogen, or some sort of carbohydrate or other organic compound that contains oxygens as well. But in both cases, we are reacting with oxygen. For the organic fuels, the products are always the same. It's a certain amount of carbon dioxide and water vapor. These are always the products of combustion when your fuel is in the form of C, H, and maybe O. Like I said before, this involves both breaking and making bonds, so it's kind of hard to get too much into the energy perspective. I like to really only focus on that when talking about synthesis and decomposition processes. So bringing it back to what we saw, well, I kind of touched on it twice. This was a decomposition, and this was a combustion. So how do we write that? Well, we have our reactants, and so we've got to make some products. If there is a combustion going on, and I recognize that this second reactant is some sort of organic fuel, we know we're going to make a certain amount of carbon dioxide and water. But if we were taking a look at this closely, I can see that there are potassiums and chlorines on the left, and they are not present in the products. But this decomposition, maybe we should talk about this separately. We had mentioned on an earlier slide that potassium chlorate does have this property where it will decompose into potassium chloride and oxygen. Oh, well, this oxygen is a fuel for the combustion of the... Oh, that's interesting. So the potassium chlorate breaks down, and the oxygen that's created is immediately used to consume the organic fuel. So it's like we have this, like, the product of the decomposition serves as a reactant into the combustion. Oh, that's an interesting reaction. So really then we have a third product here. That's this. This KCl is a product because I don't see it participating in the secondary reaction. I guess there should be a KCl here. So this one's a rather complex reaction, but hey, those are the ones that look the neatest, right? So we've got this coupled decomposition and combustion by following these patterns that we've seen in these other reactions we've seen so far. I guess we should balance it though. There you go. That looks good. So to sum things up, there are 5 main types of reactions that you need to start recognizing. What you can recognize is shown in this image here. Pretty much all the information's right there. It's based on the number and type of reactants, whether it's 2 elements, or an element and a compound, or 2 compounds, or 1 element, or a fuel and oxygen. You can put them into these general categories, which is really nice because once you can identify a type of reaction by the reactants, you could start to predict the products by following that pattern over and over again. There are some very, very rare examples that fall into 2 categories. These seem to be like these metal combustions that are also a synthesis. But in general, these groups are otherwise very separate. Thanks for watching.